In the previous class, we introduced you to this, but then let me again go back and just take a recap of what I did. That will make it easy for you to, connect things to connect things properly. Okay. So in the case of LMS, what we did, there was a input RSS, a WSS, these are the filter coefficients, output yn, you are trying to find out this filter coefficient vector W, so that yn is W transpose xn, where xn, these are all standard and we have done it so many times, but for the sake of completion I have to write every time I start teaching. So, En is dn minus yn, that is W transpose xn. We have to find out, and there is an assumption dn also WSS and xn dn, they are jointly stationary. Under that, this variance, and these are all real, so I am not putting mod en square, just simply the n square. This was, we worked out, this was sigma d square, there is a variance of d, then twice W transpose p, where p is the cross correlation vector between xn and dn, there was p was, these are all known stuff, and also there is an autocorrelation matrix. Okay, so this depends on P and R. For a fixed P and fixed R, this is a quadratic function of the filter weights because of this term W transpose R W, because R W will have elements of W present in every element of the resulting vector R W, and then that is multiplied by components of W from this side. So, that makes it second order, we all have seen this is first order term. Then the thing we do is this, we try to take derivative of this with respect to the filter weights. Okay. Find the minima, that is equate the derivatives to 0, and then we get a solution which is W opt optimal. This is indeed optimal or inverse P, assuming R to be invertible, that is positive definite we assumed. And then we try to make it adaptive, because R and P can change from time to time, okay, or their knowledge may not be available. So, we go for a steepest descent procedure, gradient descent search, because this curve is a quadratic function, it will have minima at a particular W, that is W opt, otherwise it will go up, up, up. We have to reach that minima point. So, we go for that gradient descent search, and we get that steepest descent algorithm. All right, that was in terms of R and P, that was in terms of R and P. And then we said we have to make it adaptive. So, R we replaced by a bad estimate, not so good estimate, and we substituted them in the gradient descent update equation, we obtained LMS, and because of this we pay the price. The filter weight W n does not converge to W opt absolutely, but it converges in mean. That is, every component is now fluctuating, because they are generated from the data by the LMS update equation and expected value. So, if you take the expected value at any particular nth cycle for all the weights, so this vector mean will converge this, that is every component of W n, maybe say kth filter coefficient W k n, and this W opt k. So, W k n will be fluctuating around W opt k in the steady state as n tends to infinity, that is n becomes very large. So, it will be fluctuating, so that the mean of the fluctuation is this, we can get up to this, and also convergence will become slow, all because of this fact that R and P we could not provide correct data, but we just use some approximate, so called bad approach. Now, in the case of RLS, what we do, epsilon square, we do not use this E operator. E is the root cause of the problem. The moment you bring E of xn dn, you have P. E of xn transpose R. And P and R come in all our expressions, and then in the end you give up. You have to replace R by some estimate. So, you take this bad estimate, P also take this bad estimate, and get LMS and pay those prices. We want to get rid of that E operator. Therefore, what do? We approximate this epsilon square by what? By taking many samples of E square n, E square n, E square n minus 1, E square n minus 2, E square n minus 3, all that for the same filter weight. That is, I keep giving xn, hold the same filter weight, find out yn and en. So, take E square n, for the same weight again E square n minus 1, E square n minus 2, dot dot dot, take many, add them and then average. So, if you take many and then average, that will be a very good approximation of actual epsilon square. But you see, there is no E operator, expectation operator. Okay, but the value of that will be almost equal to epsilon square if you have many samples. Therefore, on one hand, if you can plot this epsilon square against the filter weights, it will be a quadratic surface. So, if you take the sample average, that is E square n added over, averaged sample wise, if you plot that also versus W, you will get more or less the same curve, same identical curve, because for any W, the sample average will be following this epsilon square very much. That is, in the case of RLS, let me elaborate this further. Suppose we maintain the same weights, xn, yn is W transpose xn, which is also x transpose is W. All right. So, we keep the same weights, but keep sending in new and new input and find out new and new en. Okay. So, for the same weight, we find out this as, for this we take a good, sample estimate, that is E square n, E square n minus 1, dot dot, maybe E square n minus something, maybe L, and divided by how many samples? L plus 1, L plus 1. So, if L is large, this function, this function I can call epsilon square LS, least squares. This and epsilon square, they will be very close to each other. Okay, this is the actual mean square error, but has that E operator, and therefore, if you express, we have already given the expression in the previous page, that we will have R and P. That is coming because of that E operator. But suppose I replace this by a good estimate. That is this, that when I was giving you epsilon square, I kept the filter weights as it is, okay, and for that particular chosen filter weight, found out E square n, take expected value, and we got that expression, some sigma d square, we already did in the previous page, minus twice W transpose P plus W transpose R W. Okay, that was this. But it has P and R, that became because of this E operator. So, for the same W, if I keep the same W here and now keep sending data and finding out En minus 1, En minus 2 and all those, then if for a large L, if I take this average, E square n, E square, so many cases that we just square up the output error, I add them, divide by the number of terms and take let L be large. Then this will definitely, which is called epsilon square LS, this will be a very good estimate of epsilon square. So, epsilon square versus W plot and epsilon square LS versus W plot, they will be almost identical, because the two, for any W, the two values are very close, almost same, because I have taken many samples, isn't it? So, therefore, instead of reaching the minimum of this epsilon square, if I reach the minimum of epsilon square epsilon LS square, I will still be happy, I will be very close to the minimum of epsilon square. Okay. So, we try to minimize this. This is the philosophy. But by that we are getting the advantage that we are no longer using expectation operator, E operator, and therefore R and P, they will not come explicitly. All right. And this is the philosophy of RLS. So what do we do now? Let me teach more formally. Suppose we start at n equal to 0. Okay. We have a vector we have a data matrix so x0 to xn, very long vector maybe starting from 0 to n in okay. The next column will be one cycle delayed version. So if it is x0, it will be x minus 1. If it is x1, it will be x0. If it is xn, it will be xn minus 1. Next column, another cycle delayed version. So it is x minus 1, it will be x minus 2, x minus, if it is 0, so 1, 0, minus 1, 0, minus 1, minus 2, n minus 1, n minus 2, dot, 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 dot. Maybe we take up to some n minus n plus 1. Okay. So if n is 0, it is x minus n plus 1. If n is 1, dot, 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 dot. This column, for the time being only, this column, for the time being we will call it xn vector. Later xn will be used to indicate some other vector, but for the time xn. This vector, it is one cycle delayed version, right? When I have x0, that time this fellow is x minus 1. When I have x1, then x0. When I have xn, xn minus 1. So we use a notation z inverse xn, just a notation only. As this vector is delayed by one cycle. This will be and lastly all right, and let W be all right. Then tell me what this is. If I take this dn minus this xn into w, dn, start with the last component, d of small n minus last row times w. Last row times w means w0 into xn plus w1 into xn minus 1 plus w2 xn minus 2 dot dot. So, it is a filter output at nth clock. All right. So, d of n minus the filter output at nth clock for this choice of weight vector. Okay, that will be E n nth clock d of n minus, when you are multiplying x n into w, take the last row times w. So, w0 x n, w1 x n minus 1, w n minus 1 into x n minus capital N plus 1, that summation, that is the filter output at nth clock that you are subtracting from d n. So, what you are getting is E n. Then you can say d n minus 1, it will be x n minus 1, n minus 2, like that, dot, 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 dot. So, next term will be d n minus 1 minus this row, last but one row times w. So, w0 into x n minus 1 plus w1 into x n minus 2 plus w2 into x n minus 3 dot, 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 which is the filter output at n minus 1th clock. that subtracted from dn minus 1. So, it will be en minus 1 and like that dot 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 x1. So, n is 1 here at 1th clock. I have d1 minus this row second row times w. So, w0 x1, w1 x0 and dot dot dot. So, it is a filter output at clock 1 subtracted from d1. So, it will be e1. By the same logic, this will be e0. All right. So, this our purpose is to minimize how many rows here? 0, 1 up to small n. So, n plus 1 terms, right. So, if I take square up all the errors, I have kept the weight vector fixed, just running the experiment and various indices, clock indices, and finding out various errors, squaring them up, adding, dividing by the number of terms. So, this is what is my epsilon square LS. If n is large or n plus 1 is large, this will be a very good estimate of mean square error. Okay, it is a very good estimate of mean square error, but E operator is no longer present, right. So, we will minimize this with respect to weight. After all, this vector is dn minus x and w. So, this vector every term depends on w. Okay. So, now we will minimize it with respect to w. That will give me the best estimate, optimal one, and that will be close to the optimal one which we get there, because this epsilon square LS or this epsilon square, they are almost same. So, minima here and minima here, they are also same. Okay. If you plot epsilon square versus filter weights and plot epsilon square LS versus filter weights, the two plots will be almost identical to each other, because the values are same, almost same. It is a very good estimate if the number of terms is large. All right. So, our now purpose will be to minimize this. Now, denominator is n plus 1, that does not depend on w. So, we will be minimizing only this much. Okay. So, our task is to minimize the sum of square of errors. It is called sum of squared errors. Every error is squared and then sum of squared error. We will minimize this with respect to filter weights. But this is equal to, this is same as you can see, if I take this vector as En vector, this is nothing but norm square of this, that is En transpose En. Isn't it? If you take En transpose En, E0, E0, E0 square, E1, E1, E1 square, E2 square, all that, right. So, essentially we will be minimizing the norm square of this error vector with respect to filter weights. All right. So, you go to the next page. We had En, I rewrite then you have to minimize. Now, E transpose and En, replace En by this. That means so, this is a column vector after transposition row vector. So, dn transpose dn, which is norm square of dn, but it is independent of w. Then xn w transpose dn. So, this is w transpose xn transpose dn. Another one dn transpose, dn is a column vector, now it is a row vector, dn transpose xn w. And then xn w transpose xn w. So, w transpose xn transpose N W. This is what you have. Now, these two terms are same. What is the transpose of the other? Because it is a scalar. All the terms are scalar here, isn't it? Because this overall thing is norm square of Pn, which is a scalar. You can see here also, W transpose is a row vector, Xn transpose is a matrix, so row vector into matrix is a row vector, column vector is a scalar, like that. These two are same, because if you take the transpose of this, you get this, isn't it? If you take transpose, Dn transpose comes first, then transpose of this W transpose Xn transpose, which is Xn W. So, one is the transpose of the other, but both are scalar. So, scalar and its transpose, they are same, isn't it? Scalar and its transpose, they are same. So, if they are transpose of each other, okay, then they are same because each is a scalar. So, this is equal to twice this by epsilon square LS, you can see. I mean, I am not taking that 1 by n plus 1, okay, because I am taking on the numerator. So, therefore, if I take the gradient of this, I have to minimize it, right. So, we all know W transpose, this is a column vector, Xn transpose is a matrix times Dn is a column vector. So, W transpose a column vector, when differentiated with respect to W and put in a stack, it will be just that column vector. So, it will be minus twice, and this kind of things we have done many times in the past. Latest case being that case of normalized LMS algorithm and affine projection. That time also we did this kind of differentiation. And again W transpose some matrix, which is the Hermitian matrix, into W. Xn transpose Xn is the Hermitian matrix. You take transpose of it, Xn transpose, transpose, that is Xn. You get back the same thing. So, here again we know it is twice this Hermitian matrix times W equal to 0 vector. That will give me W opt. So, here WLS least squares, if this is invertible, and we will show that this is indeed invertible in practical cases, then this will be okay. So, this is Xn. There are how many columns? Capital N number of columns. Okay, there are capital N number of columns. And number of row n plus small n plus 1. Assume number of row is much more than number of column. Okay. Now, these columns we can assume them to be linearly independent easily, because they are randomly generated data. There is no linear relation involving the columns, relating the columns. Okay. So, as such we have seen Xn transpose Xn Hermitian. It's a positive semi-definite. If you take any C non-zero, any vector C, and C is length n plus 1 cross 1, okay, any non-zero vector. C transpose this matrix Xn transpose Xn C is nothing but if you take Xn C, and this is Xn C transpose, because if you take Xn C, take the transpose of it, C transpose comes first, Xn transpose there. So, that is what it is. So, Xn C, if you call it a vector D, this is D transpose. So, it is nothing but D transpose D, which is norm square. this is always greater than or equal to 0. If this is to be 0, greater than or equal to 0, that makes it positive semi-definite. So let us see when it becomes 0. If it becomes 0, extend C. If the norm square is 0, every element of the vector has to be 0, because norm square of a vector, if we call it D vector, D, xn into C is a D vector. So norm square will be d0 square plus d1 square plus d2 square dot dot dot. All are non-negative and they are adding only, no subtraction, no minus sign. So nothing like this cancels with that doesn't happen. So d0 square plus d1 square plus d2 square dot 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 added. Okay. So if that is has to be equal to 0, d0 has to be 0, d1 has to be 0, d2 has to be 0, all simultaneously. So equal to 0 occurs only when the D vector, that is x and c, is 0. But x and c 0 and c non-zero means what? If you have some elements of c non-zero, and when you are doing xn into c, you are linearly combining those columns by the corresponding non-zero elements of c and equating to 0. So that is leading to a linear relation, because then you can keep one column on one side, others on the right hand side. For instance, if all the elements of C are non-zero, so if C0, C1, C2 up to C capital N, a capital N minus 1. So xn into C will be C0 into first column xn plus C1 into second column, C2 into third column, and dot 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 equal to 0. And none of the coefficient is 0, neither C0 0 nor C1 0. Suppose that is the case, then you can happily keep one on one side, others will be on the other side. Okay, and this will be divided both by C0. So this column will be expressed as a linear combination of the other columns, and so on and so forth, which means the columns have some linear relation. We say they are linearly dependent, linear relation amongst them. But that doesn't occur in practice, because data is coming purely randomly. There is no linear binding relation on them. Okay, that's why it is safe and logical to assume the columns are linearly independent. Of course, your number of rows should be more than the number of columns. If that is not, suppose small n plus 1, there is a number of rows, there is less the number of columns. Now, if every column is in a space of dimension small n plus 1, because length is n plus 1. So you need small n plus 1 number of axis or basis vectors to express anybody. If you have more than small n plus 1, the extra vectors, they will be expressible as a linear combination of those small n plus 1 number of basis vectors or axis vectors. Okay, so that should not happen, because then again there is a linear relation. You can ask me, but we will start at n equal to 0, 1, 2, so we have to go through these stages, right? Then only we come to the very large n. Yeah, those initial stages I will take care later. For the time being, assume we are at a very large n, so number of rows is higher than number of columns. Okay. So that is why it is positive definite, so invertible. And what it means, see this, okay, you can do one thing now, bring a n plus 1 here, okay, inverse, so inverse cancels, so n plus 1, and to cancel it I will have a 1 by n plus 1. This I write as it is, that 1 by n plus 1 I write here, they are scalars, so I can write them anywhere, so this I write here. This is nothing but n plus 1 inverse, and xn transpose xn inverse. So this can go inside, n plus 1 inverse is 1 by n plus 1. This inverse, very easily 1 by n plus 1, if you take the inverse of it, it gives you n plus 1. n plus 1 and 1 by n plus 1 cancels. Now let us see what is this. Xn, you remember this was xn. So if it's xn transpose, first column will become first row, second column second one, like that. Okay. So this will be first column was xn, now it is xn transpose. Then it was Z inverse xn transpose. This is xn transpose, and xn is dot 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 dot. Now, when you multiply xn transpose by xn, what you are getting? Xn was so xn transpose xn means x0 x0 square, x1 x1 square, dot 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 up to xn xn square added, and then divided by n plus 1. So, it will be a good estimate of what? Variance. They are all 0 mean, so variance. That is, if you have to find out the variance of the data, you just square up every data, add and average, and that is what is happening. Xn transpose into xn means your x0, this is a row vector of this, so it becomes x0 into x0, x1 into x1, x2 into x2, like that. So, x0 square plus x1 square plus x2 square dot 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 up to xn square. Okay, sum and then divide by the number of terms n plus 1. So, that will be a good estimate of. So, this matrix first row first column will give you, and then 1 by n plus 1, this will be close to Rx0. Then xn transpose next guy. Next guy is here x0 x minus 1, x1 x0, gap is 1, 0 minus 1, 1 0, n minus 1. So, you are multiplying two samples at a gap of 1 and then adding them and averaging. So, that will be a good estimate of correlation with gap 1, x nth data, n minus 1th data, multiply, x n minus 1th, n minus 2th, multiply, 1th, 0th, 0th minus 1th. If you multiply and add and average, it will become next guy, this first row times next column, Rx1, and like that you can see it will be lastly Rx n minus 1. Similarly, this transpose xn is same as x transpose n, this, okay, Z inverse xn transpose xn or xn transpose Z inverse xn, they are same. So, this also will be Rx1. Then Z inverse xn transpose with itself means this vector with itself. So, x minus 1 square, x0 square dot 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 up to x n minus 1 whole square, add all of them, divide by n plus 1. Again, for large n, it will be a good estimate of Rx0. So, it will be Rx0 and it will continue. So, this will become at R matrix. So, this is getting, this matrix is becoming approximately R, and here xn transpose dn. So, if you have got dn, xn transpose dn vector was, so xn transpose, so take a transpose of it, then dn. So, x0 d0, x1 d1, xn dn. So, multiplying samples of both at a gap of 0. So, it is a cross correlation with gap 0. Okay. And then dividing by n plus 1. So, you are averaging. So, cross correlation with gap 0. So, this will be actually a matrix. First guy is that cross correlation vector 0. The next is delayed vector, this times dn. So, x n minus 1 dn, x n minus 2 dn minus 1, x0 d1, x minus 1 d0. So, it will be again cross correlation with gap 1. So, it was p, in fact, it is p minus 1, gap minus 1, n minus 1 and n. So, difference is minus 1 and dot dot dot. So, this is actually p. So, as a result, if n is large and these averages are very good averages, then WLS directly goes to R inverse P, which is W opt. So, this sum of square minimization gives you the same optimal weight if you have large number of samples. But again, you don't need any R and P in this calculation. It's all data, 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 right? Now, our purpose will be this, that suppose we have taken data up to nth clock, we found out this estimate. If I have new data, n plus 1 coming in, how will that be updated? That is the recursive least squares adaptive filter. That is what we will do in the next class. Thank you very much.